Today we're going to explain a nice connection between two numbers that seem fairly disconnected. And maybe we want to think about this as showing these two numbers are related in a certain way, like perhaps they're cousins. And well, what are these two numbers? Well, the first one is pi over 4, and the second one is the natural log of the square root of 2. And we're going to do this using some nice integrals or families of integrals. And to get off the ground, we're going to prove two fairly straightforward results. One is a power reducing formula for the tangent function, and the other one is a limit of an integral of the tangent function. So let's look at this first one. So we'll show that the integral from 0 to pi over 4 of tangent to the n power of x dx is equal to 1 over n minus 1 minus the integral from 0 to pi over 4 of tangent to the n minus 2. Okay, so let's see how we'll do this. So let's start over here with the left-hand side. So that's our integral from 0 to pi over 4 of tangent to the nth power of x dx. And then we're going to split this into two pieces. So let's, write our integral. And then we'll write this as tangent to the n minus 2 of x times tangent squared of x dx. Okay, so that's good. And then, well, I'm going to take this tangent squared and then rewrite it using a trig identity. So this is a standard strategy for getting at these power reducing formulas. So I'm going to write this as the secant squared of x minus 1. And then, well, let's multiply that tangent to the n minus 2 through and pull these apart into two pieces. So we'll have our integral from 0 to pi over 4 of tan to the n minus 2 of x times secant squared of x dx minus the integral from 0 to pi over 4 of the tangent to the n minus 2 of x dx. Now let's observe that this second integral, well, that exists exactly over here in the final formula that we're trying to get at. So that being said, we don't really need to do anything with that second integral. So for this first integral, I'm going to do something fairly tricky, and I'm going to break this into two pieces. And those two pieces are going to look like this. So the first one is going to be 1 over n minus 1 times this integral. So I'll just copy that integral again. And then, well, the second one will be equal to, well, actually just the same integral, but with a coefficient so that when I add it to 1 over n minus 1, I get 1. So it's like we're taking this and writing 1 as a sum of two numbers and then splitting this up. So in this case, what we'll need is n minus 2 over n minus 1. And then, well, like I said, this integral that we're just bringing down again. Great. And then, well, we have this bit, which, is just going to stay the same throughout our remaining steps. Okay, nice. And then from here, what we'll do is do an integration by parts on this first integral. So let's maybe do an overline of green here, and then we'll bring this over here to our little integration by parts calculation. So here what I'll do is I'll set u equal to the tangent to the n minus 2 of x. What does that make du? Well, let's recall that the derivative of tangent is secant squared, and then we'll have to employ the chain rule as well. So that's going to give us n minus 2 times the tangent to the n minus 1, or sorry, to the n minus 3 of x times the secant squared of x dx. Okay, good. And then, well, let's see. Our dv must be the rest of it. So dv is equal to secant squared of x dx, which means that v is equal to the tangent of x. Given the fact that, well, like I said before, the derivative of tangent is secant squared. So now let's use our formula for integration by parts. So that's going to be u times v, and then evaluated between the endpoints. So that's going to give us tan n minus 2 times tangent of x. And then, well, observe that this is attached to the 1 over n minus 1. So we've got 1 over n minus 1, tangent to the n minus 1 of x, evaluated between 0 and pi over 4. And then we'll have minus n minus 2 over n minus 1. So let's see, our n minus 1 in the denominator comes from this coefficient. Our n minus 2 comes from this right here where we took the derivative of u. And then, well, let's see, if we have v du, which is the next part of the integration by parts formula, let's see, that's going to be tangent to the n minus 2 times secant squared. So here we have the integral from 0 to pi over 4, tan n minus 2x secant squared x dx. And that's all from this first overlined green integral. So perhaps we'll write that down as this thing spreading out into these two pieces. And then all we have to do is bring down the next two terms. So let's see, I'll just bring those down real quick. But now, well, something magical happened, and I picked up two copies of the same integral with equal but negative coefficients. That means we get cancellation. So this term and this term cancel, and then all that's left to do is to perform this evaluation here. So the tangent of pi over 4 is 1, that's well known. The tangent of 0 is 0. That means that this evaluation turns into 1 over n minus 1. Those two middle terms, like I said before, canceled, so we just bring down that rightmost integral, which is the integral from 0 to pi over 4 of the tangent to the n minus 2 of x dx. But now let's look over here and see what our goal was. Oh, and that's exactly what our goal was, so we've got this first lemma proved. Okay, now we're ready for this next bit. We'll show that the limit as n goes to infinity of the integral from 0 to pi over 4 of tangent to the n power of x dx is equal to 0. Okay, so in order to motivate what's going on here, let's make a little bit of a picture of the tangent function. So let's go over here and put maybe negative pi over 2, and then also pi over 2. Those are the well-known vertical asymptotes of the tangent function. That's because tangent is sine over cosine, but cosine is equal to 0 at pi over 2, whereas sine is equal to 1. Okay, then let's also put some other points on here. Let's put pi over 4 here, and then maybe over here we'll put minus pi over 4. We in fact don't need anything to the left of the origin, but I'm just writing that in kind of for completeness. And then, well, I'm going to put the number 1 here on the y-axis, and then I guess I need to put the number -1 down here on the negative y-axis as well. Okay, so now let's recall that tangent of pi over 4 was 1. We in fact just used this. Tangent of negative pi over 4 is -1. And then this thing is asymptotic. So let's see if we can get our picture. So it looks something like this. Okay, so I think that's pretty good. Now let's draw two lines here. So the first line will be the line y equals x. So the line y equals x is going to look a little something like this. And then the second line will be between the origin and then this point pi over 4, 1. So that's going to look something like this. Good. So that's going to be the line y equals 4 over pi times x. And, well, the important thing to notice is between 0 and pi over 4, this graph of the tangent function lives between these two lines. So in other words, what we have here is for all x on the interval from 0 to pi over 4, we have x is less than or equal to the tangent of x, which in turn is less than or equal to 4 over pi times x. Of course, this isn't a proof. You would maybe prove this using the second derivative of the tangent function, showing something about the concavity. And then when you know something about the concavity, you know when a secant line is above the graph or a tangent line is below the graph or something like that. Okay, so anyway, now let's raise this to the nth power, and we'll have x to the n is less than or equal to tangent to the n of x, which in turn is less than or equal to 4 over pi to the n times x to the n. But now we can integrate both sides of this, or all three sides of this. So integrating 0 to pi over 4 of x to the n dx. So that's got to be less than or equal to the integral from 0 to pi over 4 of tangent to the n of x dx, which in turn is going to be less than or equal to the integral of this bit over here to the right. Okay, but then observe that this extreme left-hand side and then this extreme right-hand side have fairly simple antiderivatives. So plugging all that in, what will we get? So let's see, here we're going to get 1 over n plus 1, and then we'll have x to the n plus 1 evaluated at the endpoints. That'll give us pi over 4 to the n plus 1. So that's going to be less than or equal to our goal integral. So let's bring that down, which in turn is less than or equal to what we get from this last bit. Notice that it's essentially the same thing as over here on the left-hand side, just multiplied by 4 over pi to the n. So that's going to leave us with 1 over n plus 1, and then a pi over 4, because a bunch of that stuff cancels. And then from here, what we'll do is take the limit as n goes to infinity. Notice that this extreme left-hand side tends to 0 as n tends to infinity, kind of for obvious reasons. Notice that pi over 4 is less than 1. So this part goes to 0. And then 1 over n plus 1, well, that also goes to 0. Furthermore, this right-hand side, for similar reasons, approaches 0. But then by the squeeze theorem, since this object, our goal object, is bound between two things that tend towards 0, that means it also tends towards 0. But look, that's exactly what we needed to do. Okay, so we just proved these two things about the integral of certain powers of the tangent function, but that doesn't seem to go up here to what I originally said was our main goal, was to show that these two numbers, pi over 4 and the natural log of the square root of 2, were related. So, well, how can we do that? Well, of course, we're going to use these two, otherwise there wouldn't be much point in doing these two, starting results. Okay, so let's go here and look at the following integral. So it'll be the integral from 0 to pi over 4 of tangent to the 2n of x dx, where I've written that as 2 capital N. So let's use this rule right here and see what we get. So that's going to give us 1 over 2 to the capital N minus 1 minus the integral from 0 to pi over 4 of tangent to the 2n minus 2 of x dx. And then, well, maybe you can see where we're going to go from here. Now we can apply this rule again, where the role of this lowercase n is now 2 times capital N minus 2. So that's going to give us 1 over 2n minus 1 minus 1 over 2n minus 3 plus the integral from 0 to pi over 4 of the tangent to the 2n minus 4 of x dx. But now we can repeat this until we go all the way down to the ground, if you will. So let's see, I'll write this as equals dot dot dot, and so we'll have 1 over 2n minus 1 minus 1 over 2n minus 3. The next one will be plus 1 over 2n minus 5 minus dot dot dot. And then, well, let's observe that we subtract 2 each time. We started with an even exponent, so that means eventually we'll hit 0. And, well, just before we hit 0, we'll have, plus or minus 1. So in fact, what we'll have is plus minus 1 to the n minus 1, times 1 over, well, 2 times n minus whatever we need to subtract to get the number 1. And then the very last term will be plus minus 1 to the n, and then our integral from 0 to pi over 4 of, well, simply dx. Okay, great. But that last integral is exactly equal to pi over 4. So I think that's pretty clear. Okay, so, well, let's see what we can get out of this. So if we maybe factor out a certain power of minus 1, we'll have minus 1 to the capital N minus 1 times, so this will be the sum as little n goes from 1 up to capital N of, let's see what we have. We'll have minus 1 to the n plus 1 over 2 times little n minus 1. So, well, what is this term capturing? Well, this term right here is capturing all of these. So notice that we've got this alternating sum of reciprocals of odd numbers that we got, well, from these tangent integrals. And then, well, this last bit will end up being minus pi over 4. Okay, so that's cool. But now let's take the limit. So if we take the limit as maybe capital N goes to infinity, what do we get? Well, let's observe that this left-hand side will go to 0. That means this right-hand side also goes to 0. I guess I should say that all of this is equal to our integral from 0 to pi over 4 of tangent to the capital N, or capital 2, to the 2 times capital N of x dx. So rewording this, as the capital N goes to infinity, that right-hand side goes to 0. That means this left-hand side goes to 0. That means that this stuff inside of the parentheses goes to 0. And we're left with the sum as little n goes from 1 to infinity of minus 1 to the n plus 1 over 2 times n minus 1 equals pi over 4. So this is the famous formula that says the sum of the reciprocal of the odd numbers is equal to pi over 4. So let's copy that down here. So we have pi over 4 is our sum as little n goes from 1 to infinity minus 1 to the n plus 1 over 2n minus 1. Okay, so, well, motivated by this, let's see what happens if we start with an odd power of tangent here. Okay, so now we're starting with an odd power of tangent here, like I said we would. And, well, we're going to play this rule again. So that's going to give us 1 over 2 times capital N minus our integral from 0 to pi over 4 of the tangent to 2 capital N minus 1 of x dx. Well, and now we're going to do this again and again and again. So the same kind of thing is going to happen. We'll have 1 over 2 times capital N minus 1 over 2 times capital N minus 2. The next one will be plus 1 over 2 times capital N minus 4, all the way down to plus minus 1 to the capital N minus 1 times a half. That's our next to last term. And then the very last term will be plus minus 1 to the capital N, and then the integral from 0 to pi over 4 of the tangent of x dx. So observe here that, well, we're going to end up with a single power of tangent because we're decreasing by 2 each time, starting with an odd power. So, well, let's observe that this is fairly straightforward to evaluate as well. The antiderivative of tangent is the natural log of secant. We don't need an absolute value there because, well, between 0 and pi over 4, secant is positive. Then secant of pi over 4 is the square root of 2 because it's 1 over cosine. So that's going to end up giving us the natural log of the square root of 2. Okay, well, let's see what that ends up giving us. So bringing everything down like we did before and factoring out a minus 1 to the capital N, we'll have the following, or maybe a minus 1 to the capital N minus 1. So we'll have the sum as little n goes from 1 to capital N of minus 1 to the little n plus 1 over 2 times n minus the natural log of the square root of 2 is equal to our integral from 0 to pi over 4 of the tangent 2 times n plus 1 of x dx. But now, just as we did before, we'll use this second rule that says this limit of the powers of the tangent function integrated like this tend towards 0. So this tends towards 0 as n tends towards infinity. That means that all of this stuff in the parentheses also tends towards 0 as capital N tends towards infinity. And that gives us our second rule, which is the reciprocal sum of the alternating reciprocal sum of the even numbers is equal to the natural log of the square root of 2. So let's bring that over here. So natural log square root of 2 is equal to the sum as n goes from 1 to infinity of minus 1 to the n plus 1 over 2 times n. Okay, well, I think this itself is a nice result, and we've maybe answered this question up here of how pi over 4 and the natural log of the square root of 2 are cousins. That being said, I'd like to finish this thing off by doing one more nice little calculation, tying everything together a little bit more tightly. Okay, so now we're going to tie everything together. So I'm going to strangely look at the object minus natural log of the square root of 2 plus I times pi over 4. So what'll that be? Well, I'm going to write this natural log of the square root of 2 using this formula down here. And then I'm going to write pi over 4 using this formula right here. So what will that end up looking like? So we're going to have I, and then minus 1/2. And then next we'll have minus I over 3. And then next we'll have plus 1/4. And then next we'll have plus I over 5. And then minus 1 over 6. And then minus I over 7. And then plus 1 over 8. And then so on and so forth. So notice that we've got these different chunks. 2 negatives and then 2 positives. 2 negatives and then 2 positives. But then we're also alternating between real numbers and imaginary numbers. And what's going on here is what we're really seeing here is different powers of I. So let's recall that I squared is -1, but that means that I cubed is equal to -I, and I to the 4th is equal to 1. So rewriting this, what we in fact have is the sum as n goes from 0 to infinity of I to the n plus 1 over n plus 1. So the 0th term will give us I to the 1 over 1, that's this. The first term will give us I squared over 2. Well, I squared is -1, so we get -1/2. And then everything else follows from there. But now let's rewrite this as follows. This is equal to the sum as n goes from 0 to infinity of, well, this looks like z to the n plus 1 over n plus 1 evaluated from 0 to I. But I like to think about this evaluation as a 0th integral. We can change that to a first integral by applying the fundamental theorem of calculus and taking the derivative. So that'll give us our integral from 0 to I of the sum as n goes from 0 to infinity of z to the n dz, because the derivative of z to the n plus 1 over n plus 1 is z to the n. Oh, but check it out right here. This sum as n goes from 0 to infinity of z to the n is in fact a geometric series where a common ratio is equal to z. So, well, we can rewrite this as the integral from 0 to I of 1 over 1 minus z. That's using the geometric series summation formula. But then that has a fairly straightforward antiderivative, minus natural log of 1 minus z. But then plugging in I, we get minus natural log of 1 minus I. And then, well, looking from the extreme left-hand side to the extreme right-hand side, we have this nice formula that we've built for the natural log of this complex number. Now, of course, logarithms of complex numbers can be defined for any complex numbers. And in fact, I think I made a previous video about that. You should check that out. If you'd like to, it should be on the screen now, and that's a good place to stop.